So I have two last part of chapter 6. Okay, how do you use the facts before to decide how many subgroups or how many elements in a direct product of groups. So are some questions, and then there is a last part. I mentioned in the last class that you cannot find the order of UN. Okay, the order of Zn is just n, but what is the order of Un? Okay, that one, there is a way. Okay, so I'm looking at an example in the book. Okay, now there's one example, 6.7. Example 6.7. Right? Determine the number of elements of order 5 in Z25 plus Z5. Okay. Determine the number of elements of order 5 in Z25 plus Z5. All right. So let G be Z25 plus Z5. Okay. Now, you want to find the number of elements of order 5. Somebody cannot hear me still? Iman? What about the others? Ain, can you hear me?
I cannot hear you clearly.
Hey, this is weird. What happened to my... Cannot hear clearly?
Yes, just slow voice from my meeting, from my video.
What about the others? Ahmad also. Cannot hear? You okay? Hassan is clear? It must be you.
I think I leave the meeting first and I log in.
Okay, okay. If nobody can hear me, means something wrong with me. If it's only you. Okay. Okay. Everyone else is okay? You can reaction button.
Yes, Doctor, very clear.
Ah. Okay. Okay, so she's coming back, so make sure you let her in, yeah? Okay, so we want to find elements in Z25 plus Z5 that has order 5. How many elements in G? So what is the order of G? 25 times 5, which is 125. So before this, what we do is we can list all elements and then find one by one the order. Okay, but what if there are 2,000 elements in the group? Okay, this is, let me do my WhatsApp first. The setting, notification, turn off, mute. Fine. Okay, disturbance. Okay. Okay, so we don't want to list all 125. Okay, so what we will do is we use the fact that the order is the lowest common multiple. We don't want to list all, yeah? So let G be G1, G2. Okay, since any G in the direct product has to be a pair in G. Okay, so G1 will be in Z25, G2 will be in Z5. Okay, so what is the order of G? The order of G is the LCM, the order of G1 and G2. Okay? The order of G is the lowest common multiple, the order of G1 and G2. And since G1 is in Z25, the order of G1 has to be dividing or factors of. So 1, 5, factors of 25. 25, right? And G2, since G2 is in Z5, so it's a factor dividing 5, so it's 1 or 5. Now, we want it to be 5. That's the question. Determine the number of elements of order 5. So you have to determine LCM of this and this is equal to 5. Okay? So, what's the cases? Okay, so I put like this. G1, G2. Okay, case 1. LCM of what is 5? 1 and 5, right? 1 and 5. Case 2. 5 and 1. LCM 5 of 1 is 5. Case 3. LCM 5 and 5 is 5. Okay, that's it. So we have only 3 cases. We have only 3 cases. This is just the cases. It's not the number of elements. Okay. Okay, now I haven't given you this before, but I don't know if you realize this, that okay, that, so I think this is clear. Okay, if K is in Zn, the order of K is N over GCD and K. Let's look at this. Like Z6. If the GCD is 1, if the, who's coming? If the GCD is 1, the order of K is N, meaning it is a generator. Okay, that is a theorem, right? If the GCD is 1, it's the generator. Okay, so what is the generators? That will be 1. 1, 5, right? The order. Okay, this has order 1, this is order 6, this has order 3, this has order 2, this has order 3, because 4 times 3 is 0. Why is coming in and out? Admit that. I don't know, I can cross. Okay, so 5 is GCD is 1. 5 and 6 GCD is 1. So the order is the same as the order of the group. Okay, now how do I get this 3? Just now, because I know 2 plus 2 plus 2 is 0. But if I want to use this, okay, if I take 2 in Z6, 2 in Z6, the order of 2 is 6 over GCD 2 and 6. 6 over 2 is equal to 3. It's coming in. Nampak tak? Huh? Already inside. Okay, admit. Okay, so now try with 3. Okay, GCD 3 and 6 is 3. 6 over 3 is 2. There's another way, because sometimes it's not this easy. Okay, sometimes, let's see. This, I give you this question. What is the order of 112 in Z 300? What is the order of 112 in Z 300? You don't want to multiply, right? How many times? You don't want to find all factors of 300. There's many. So using this formula, the order of 112 is 300 over GCD What is the GCD? How do you find GCD? How do you find GCD? Yeah. One way is to do like this, right? I think 4. You can divide by 4, right? 4, yeah, right? 4 times 28, right? And 75. Right? Can you find any more? No, right? So the answer is 4. So the answer is 75. Or you multiply 112 by 75. It's a multiple of 300. And now what's 112 times 75? Your phone is the 8400. If you divide this, is 28. Okay, so yes or no? Yes, okay. So That is how you find the order of K in Zn using this. Alright, I didn't give you this before. Just if you've seen it somewhere. Okay, why do I do this? Because I want to figure out how many, yeah? Okay. Okay, so G1, I will list. I don't put how many, but I will list. How many element, not how many, what are elements of order 1 in Z25? There's only one, right? Which is 0. Okay, identity. That's only the identity. Okay. Now, this is in Z25. This is in Z. Okay, now how many elements of the 5 in Z5? We have 1, 2, 3, 4. In ZP, since it's prime, all numbers right? Okay, the generators of Zn are those in which K and this GCD is 1. The generators K of Zn are those in which the GCD is 1. There's a theorem in chapter 3. And K is actually element of Un because it's relatively prime. Okay, elements of Un. And for Z5, U5 is 1, 2, 3, 4. Exactly. Yeah. Okay. For this, it's a little bit tricky. Okay. You want to find element in Z25 of order 5. Okay. G in Z25, G is 5. So if you remember this, and we want this to be 5, the order is 5. You want to find K. Okay, you want to find K. So what you have is $25, yeah? 25 over GCD K and 25 equal 5. This implies GCD K and 25 equal 5. Okay, this implies K is, what is GCD? In numbers in between 0 to 24, the GCD is 5. That will be 5, 10 with 25, right? 5 is 1 times 5 with 25. The GCD of 5 and 25 is 5. The GCD of 10 and 25 is 5. Then 15, right? And then 20. This is the fastest way to count. You don't want to count one by one by one. So I put here. Okay? The rest is easy because order 1 in Z5, there's only identity. This one you just copy. Okay, so number of elements. So that's 1 times 4. 1 times 4. 4 times 1. 4 times 4. So the answer is 24. Okay, so you can see page 91 here. In the case, these two, I put there are 4 choices of A and 4 choices of B. Okay, so I didn't give you the detail. This is more detail. Case 2, 5, 1. I have 4 choices here and only 1 here because of the identity. And the case here, this is the identity, this is the others. Okay, so you don't have to list this if the question just asks you how many elements. But I want to show you what are the elements. Okay, if the question is how many, then you can just write how many. Next question, if they want to ask you to list all 24, can you list all? You imagine there are 125 elements in here, and there are 24 elements of order 5. The others would be 1, 5, 25, right? Because all must be dividing 125. So if you have to list all 24, you will list 0, 1, 0, 2, 0, 3, 0, 4. All right, that is a pair. Then you will list 5, 0, 10, 0, 15, 0, 20, 0. That's another 4. And then you will list 5, 1, 5, 2, 5, 3, 5, 4, dot, 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 21, 22, 23, 24. That will be another 16. Okay, so we have had 24 elements of order 5. Okay, the next question that you probably will be asked is that give 3 different cyclic group of order 5. Okay, give 3 different cyclic group of order 5. So the easiest way to find a cyclic group is to find one element of that order. Okay, but you have to make sure they are all different, because if you take any from here, this element, these 4 elements here, they will generate the same cyclic group. These 4 elements will generate the same cyclic group. Okay, so you have to take one from here, one from here, one from here. Okay, so I add another question. Just now the answer is 24, yeah? To the first question. Next question. What's the next question just now? That's number 1. That's number 2 is find 3 cyclic subgroups of order 5. Okay. So I just take one from here, generated by 0 and 1. And list all elements. Okay. So this one, okay, wait. this is the identity, 0 times. Remember, this is Z5 plus Z25. So the operation is addition. You add. Okay, so the first one is multiplying by 0. Okay, you remember this? So if addition, you multiply because it's G plus G plus G. Okay, so the first one is 0. The second one is this. Then add again. Add again. Add again. You remember it's Z25 plus Z5. So the first component is modulo 25. The second component is modulo 5. Oh, I didn't ask Iman just now. Imanina?
Yes, I can hear.
Okay, so it was the problem of your...
Yeah. I changed to I changed to phone. I use Zoom by phone.
Oh, okay. Because last time you use your laptop, it's okay, right?
Never mind, I will check.
Okay. Later on, you can still watch the recording, right?
Yes.
Tan, are you here? Why I keep seeing you entering waiting room? Huh? Did you see? Tan is on campus, right? Tan? Tan is having a hard time to join in. But next week, I will invite Tan to come over to my office. I don't see Tan inside. Okay. I don't know. Sometimes it's okay. Sometimes, before I forget, for the test, we don't have to go into Zoom. Then we see Tan is entering again. I don't know. Maybe something is wrong with the internet and so on. I will spend some time to mention about our test, yeah, at the end for the class. Let me finish this first. Okay. Later on, I show you record. He's still there. Okay, so add another one, right? Okay. The other one is 50. I erased the question, but this is the question, right, Anna? Right? Okay, so the first component is 25, the second component is 5. So again, I normally will start with the identity, but you can start with the first one. So 50, add 50, add 50, add 50, add 50, you get this. So this is secret. The third one, you can pick 20. Okay, you can pick any of this. Am I still inside? Suddenly, I don't see anyone. Okay. Okay, you can pick any of the 4, but they will generate the same cyclic subgroup. Okay, if you take 10, you will add again, you will get 20, and then 30 is 50, and then add again 10 is 15, you will get the same thing. But I will take the smallest one. The third one will be 5, 1. Right? So 0, will be the identity. 5, 1, 10, 2, 15, 3, 24, and then 5, 1 will be 0, right? So if you pick 21, you will get also Okay, they generate the same thing. Okay, so what we have seen is to find how many elements of certain order in the direct product. If there are 3 components, then you have to find LCM of 3 components. Okay, so probably there will be more cases, but it will increase. If there is 3 and the answer is 5, you can have many combinations, like 1, 5, 5, or and so on. Okay, so this is the way to find elements of certain order, generate the element, becomes cyclic group. Now next one is a little bit different. Okay, find subgroups, not cyclic subgroups. I want to show one theorem. Okay, theorem 6.2. I mentioned this in the previous class. I'm not sure if you realize or not. Let G and H be 2 finite cyclic groups. Then G plus H is cyclic if and only if their GCD is 1. Okay? For example, Z2 plus Z3 is cyclic. Because there will be element inside of order LCM 2 and 3, which is 6, which generate the whole group, right? So it's cyclic, and you can show that this is isomorphic to Z6. Okay, this is chapter 5. They are not the same, but they are isomorphic. Why are they not the same? Because the elements are different. The elements here are pairs, right? The element here is just singleton. So how do you show that they are isomorphic? If you want to list the elements, that would be 0, 0, 1, 0, 0, 1, 0, 1, 2, 0, 0, 0, 1, 0, 2, right? 1, 0, 1, 1, 1, 2. Okay, this one is 0, 1, 2, 3, 4, 5. This is 0, 1, 0, 1, 2. Now, we want to map. We want to map the identity to the identity. I know that this is the generator and the generator. So the generator of the direct product, if G is generated by G and H is generated by H with GCD GH equals 1, then this is generated by the generator. It has to be cyclic first before plus the GCD, then cyclic. Okay, it has to be cyclic. This is cyclic, this is cyclic. The GCD is 1, so this is cyclic. So this is cyclic, this is cyclic. The GCD is 1, so this is cyclic. And the generator is the generator of G and the generator of H. Okay, so I know the generator of this is 1, right? The generator of this is 2 or 3, 1 or 2. Right? It has all elements of, this is P prime. So all elements have order P. Okay, so this is a generator I can map. Okay. Yeah, this is order 6, right? This is order 6. This is order 3. Okay. This, what is the order? LCM of 2 and what this is order 2. LCM of 2 and 3 is 6. LCM of 2 and 3 is 6. What is the order? The generator here is 1, 2, 3, 4, 5. Only 2, right? So let me put, before you get confused. I got confused too. Put the order. 1, 6, 3, 2, 3, right? 3, 6. 1. LCM, this one is all 1. So this one is 1. This is 3, 3. 3, 3. This one is 2 and 1. 2. This one is 2 and 3, 6. This one is 2 and 3. 2 and 3, 6. Okay. So let me redo. Different color. So we have to map the one with the same order. Order 1, order 3. There are 2 order 3, so you can pick any one. This is another one, order 3. Okay. Order 2, there's only one order 2. Okay, now order 6, order 6. So there are possibilities because you can go order 6 here, here, or here, here. Okay, both will work. And then this is 1 to 1 on 2, and then you have to show preserve operation. Okay, so by theorem, you don't have to show. By theorem is cyclic, so it's isomorphic to Z6. Now, another example or counter example is that, what about Z2 plus Z2? Is this cyclic? Is not cyclic because the GCD is not 1. Okay, this is cyclic, but the GCD is 2. It's not 1. Why is it not cyclic? So this is not isomorphic to Z4 because there is no element of order 4. Why not? Because elements in here is of order 1 or 2. Element in here is of order 1 and 2. LCM of 1, 2, 1, 2 cannot be 4, right? It will be 1 or 2. So all elements will have order 2. Okay, so that covers this one. Right? Now, I want to go to example 6.8. 6.8. There will be more example, but in the exercise, let me just go one, and then I go to the last part, right? Find all subgroups of order 15 in okay. One way to find a subgroup that G is Zn plus Zn. If you realize we're going to give example only on Z, because it's much easier to find the order of the element. If I give you U or matrix, then it's not that straightforward to find the order. Okay, so if I give you this, if H is a subgroup of G, then H is actually the direct product of H1 and H2, such that H1 is a subgroup of Zn, H2 is a subgroup of Zn, and that the order of H1 divides M, the order of H2 divides N. Okay, so if you have a subgroup of the direct product, you also have terms of a subgroup in which the first component is a subgroup of this, the second component is a subgroup of this. So back to the question. So if call this G, so if H is a subgroup, then H1 will be a subgroup of Z25, H2 a subgroup of Z5, and the order, I haven't finished, and the order of this is the order of this times the order of this. And it has to divide the order of the whole group, right? Because it's a subgroup. Okay, this is the order of the group. It has to divide. Okay, now we look back in the example. So we have something H. So H1 is order dividing 25. H2, the order is order dividing 5. Don't get confused with the LCM, because this is a direct order. It's an order of group, yeah, not order of element. Can you multiply H to get subgroup of order 15? Is that a way to multiply to get 15? Impossible, right? 1 times 1 is 1, 5, 5, 25, 25, 125. So there is no subgroup of order 15. That is what is given in the example. If I change the question, Hannah, take a note. My next example in my next notes is change 15 to 25. Okay? If I change the question to 25, change the question to 25. Now I will get the answer. get the answer? What is it? Question 25, right? So case 1, 25 and 1. 25 times 1. Case 2, 5 times 5. Okay? So you want to write the subgroup. What is the subgroup? What is an element of order 25 in here? I can put 1. What is the element of order 1 in here? Identity, right? Okay. What is the element of order 5 in here? What is the element of order 5 in here? So I already get 2 different subgroups of order 25 in here. My next question is, are they cyclic? Hannah, are they cyclic? You remember? They are cyclic if this is cyclic, and the GCD is 1. Okay? The GCD here is 1. So you can actually write this as this. So this is actually a cyclic subgroup of order 25. Okay? This one is order 25 because this is order 5, this is order 5. You can multiply. But this is not cyclic because the GCD is 5. Okay? You cannot put this as this. This is a subgroup of order 5 because GCD is 5. Right? If you write out, multiply out, you get only 5. But this is a subgroup of order 25. So this is a subgroup of order 25, which is not cyclic. Okay? So I don't want to write this. Okay? So non-cyclic subgroup of order 25. It's not cyclic because the GCD is 5, not 1. Right? It's cyclic because this GCD is 1. Okay. Guess I have to stop here. But I still have one last one. Okay. Let me go real quick. Let me go real quick to the last 2 theorems so you can finish after this Wednesday, because this Wednesday will be your test. After that will be next week on Monday. Okay, so in the meantime, after your test, until Monday, you can do all exercise because Monday we will go into the next chapter. You can try all exercise for chapter 5 you have handed in. Chapter 6, yeah, you can just do, don't need to hand in. Let me go through the last part. Okay, I mentioned that for Zn, the order is n, but for un, it's not n, right? There is no formula. Okay, so in the last session, we want to try to find the order of un. So the first theorem says, let m be written as n1, n2 until nk with GCD and I and j is 1 for I not j. Then you can write um isomorphic to these uns. Okay, so what we will do is we will write the order as a product of powers of primes. Okay, we will write the order as product of powers of primes so that the GCD is always 1 in between. So for example, U05, 105. So 105, you break up into prime. Okay. So 3 and 5, 3 and 7, 5, they are all prime. Okay. So you can, this is equal, yeah? Isomorphic to U3, U5, U7. Okay. Or you can take any of this, because this and this and this, this and this, because they're all prime. So you can write like this. Okay. Now, next is you have this formula. U2 is always isomorphic to Z1. And U2 to the n is isomorphic to Z2 plus Z2 to the n minus 2. This one is a typo, yeah? It's 2. Okay. UP is isomorphic to ZP minus 1. And U of P to the n is isomorphic to ZP to the n minus P to the n minus 1. So this one, U3, is isomorphic to Z2 P prime, yeah? Plus Z4 plus Z6. Okay? Because if it's P prime, odd prime actually. Because if it's 2 is here. Even if P2 is, I just put P prime then. Because if P2 you get. Okay, so then from here you know this, right? 2 times 4 times 6. 48. So you don't have to list all the elements. Now, last one. Find the order of U3000. Because I love U3000. That's the movie. If I give you this in your second test, I don't want you to list 1, 5, 7 until 2999. Okay? So, what will you do? So, 3000. Okay, U3000 is U. How do you do this? 3000. If you do like this, break up into big ones. Okay, 30 times 100, right? 3000, right, Hannah? So 3 times 10 times 10 squared, right? Right, 3 times 2 times 5 times 2 squared times 5 squared. So I get 2 cubed times 3 times 5 cubed. Anna, can you double check? 8 times 3, 24, 24 times 125. 24 times 125. Rather than you divide by 2, by 2, by 2, you break up into big portion and then break up. This is what I do. So this is isomorphic to U2 cube plus U3 plus U5 cube. Okay, and this is isomorphic to here, right? 2 cube. Z2 plus n is 3. 3 minus 2 is 1. Okay. And then U3 is Z2. Okay, I erase here. And then U5 cube is 5 cube. Just now is 2 cube. 5 cube is here. 5 cube. So 5 cube minus 5 squared. Okay, which is equal to Z2 plus Z2 plus Z2 plus Z. 125 minus 25, right? So U3000 equal 800. Please double check my calculation. Oh, I'm out of the radar. Okay. All right. So you can do all questions, okay, in the chapter.